All right, here we go. So lesson 15 is on exponential and logistic functions. So exponential functions are things that you should be very familiar with. There are things that are like y equals 3 to the x. We know how to graph exponential functions. The thing that we have never seen before, most likely never seen, are logistic functions. Okay, so we're going to learn about those today. All right, so let's start with the basics with exponential functions. So an exponential function can be written in two different ways. You might see like f of x equals a to the x, or you might see f of x equals p times a to the x. Okay, so there can be a number out front as well, a coefficient. If a is greater than 1, we have exponential growth. Okay, so that means that the graph is going to go up. So if a is greater than 1, you're going to go through the y-intercept of 0, comma p, and we'll talk about why that is. And it's going to go up like this. The thing to notice is that it has a horizontal asymptote of y equals 0, and it's unbounded on the right side, meaning it's going to, the limit as x goes to infinity is going to be infinity. It goes up forever. All right, then if we have something that's called exponential decay, that's when you have an a value that's between 0 and 1. Okay, so a could be like 1/2 or 3/4, right? So what it looks like is it still goes through 0, comma p, but it goes down. So now on the right side, we have a horizontal asymptote of y equals 0, and on the left side, it's unbounded. So if I was writing out the end behavior, I know you guys love when I talk about limits, I would say the limit for the first one as x goes to infinity of my function is infinity, but the limit as x goes to negative infinity of my function goes to 0, right? It doesn't go to negative infinity, it goes along that line. So as I go to the left, I'm going along the line y equals 0. Same idea for the one over here, so I'm going to say limit as x goes to infinity. So as I go to the right of my graph, what's f of x go to? 0, it gets closer to the x-axis. And then as I do the limit as x goes to negative infinity of my function, I go to infinity. So I'm going up. All right, so these first examples, it says find the exponential function f of x equals p a to the x whose graph is given. Okay, so in Algebra 2, we always had very, very nice numbers. You may not have very, very nice numbers in pre-calc. So this first one is an example of one that's not really the nicest. But we're going to talk about different forms for the answer because that will be very important as you guys have the PSAT quickly approaching, right? You need to know how to write things in different forms because maybe, you know, you look at your multiple choice and you're like, my answer's not there, but it really is there, right? So here's what we're going to do. So we're going to have f of x equals p times a to the x. And the first point I always want you to use is the y-intercept. Okay, notice when you plug in 0 for x, oops, a to the 0, you're getting 3 for the y. So we have 3 equals p times a to the 0. What's a to the 0? 1. So we get 3 is equal to p times 1, or 3 equals p. Okay. I'm using this point for my x and my y. So I plugged in x is 0 and y is 3. All right, once you get what p is, we do a second part of the problem. So again, we go back to our f of x equals p times a to the x, but now we know p is equal to 3. So we have 3 times a to the x. And we're going to use that other point. So we're going to use this 3, comma 48. So I'm going to plug in 3 for my x, and I'm going to get 48 for my y. So when I divide by 3, 48 divided by 3 is 16. So I get 16 equals a to the 3. And so if I want to solve for a, I have to take the cube root. So I'm going to take the cube root of 16 equals a. Now with the cube root of 16, we actually don't leave it like that. It's kind of like if I had like the square root of 8. Square root of 8 is 2 root 2, right? We always write it like 2 root 2. Same thing here. Do you guys remember if you have 16, it's 2 times 2 times 2 times 2. So when I take the cube root of something, I'm looking for any set of 3 that I have. Do you guys see that? I have 3 2's. So that 2 times 2 times 2 is 8. So when I take the cube root of 8, I get 2. So it's really 2 cube root of 2 is equal to a. So it's a weird base. So that means that our function is really weird. Our function is going to be f of x equals 3, right, that was the p, times 2 cube root of 2 to the x. Okay, that is a terrible form. Like, I would guess that no multiple choice test will ever have it like that. Okay, so I'm going to show you how I think multiple choice tests would write it. They would probably use this cube root of 16, but instead of writing the cube root of 16, what they would probably do is 16 to the 1/3. Do you guys understand that? 16 to the 1/3? Right, do you see how that's cube root? Then what do you think that they would do with these powers? You multiply them, right? So it's going to be f of x equals 3 times 16 to the x over 3. That's how I would write it if I was writing a multiple choice test. So it's a little bit weird, right? All right, so number 2. Not much space for number 2, but we got it. The number 2 is much easier. I should have done it first. All right, so number 2, is it exponential growth or decay? Decay. So already we know that our answer that we get for A is going to be between 0 and 1. Okay, because it's decaying, it's going down. Okay, so as I'm doing this, I'm going to set it up with my f of x equals p times a to the x, and I'm going to plug in that first point, the 0, 4. So when I do that, I have p times a to the 0 equals 4, 0, and I end up getting 4 equals p. What are you noticing? P is always what? The y-intercept. Okay, so you can skip that first step if you recognize that. That's why up in the picture above, right, I wrote 0, p was the y-intercept. All right, so we have f of x equals 4 times a to the x. All right, so we're going to use that other point to find what a is. So I have 16 when I plug in x equals -2. So I'm going to divide the 4 over, so I get 4 equals a to the -2. What's a to the -2 mean? No? 1 over a squared, right? So 1/2 would be a square root. It's -2. It's 1 over a squared. So I get 4 equals 1 over a squared. So I'm going to think of it as 4 over 1 equals 1 over a squared. So you could cross multiply. If you cross multiply, you get 4 times a squared equals 1, and divide by 4, and so on. But what I like to do when I get it in this form, 1 over a squared equals 4, is I just take the reciprocal of both sides. Right? Does that make sense? If 1 over x is equal to 1 over 2, doesn't it make sense that x is 2? Do you understand what I'm saying? So you're going to flip both sides. So we get 1/4 equals a squared. And then we take the square root. So when I take the square root, I do plus or minus. I get a equals plus or minus 1/2. Okay, for exponential functions, you're never going to have a base that is negative, ever. I'll show you why, but we're never going to have a base that's negative, so a is going to be positive 1/2. So that means our final answer is f of x equals p, which was 4, times 1/2 to the x. That's it. Okay, can you multiply the 4 and the 1/2? No. Why? Right, the 1/2 is attached to that raised to the x, right? If I was plugging a number in, I always have to do my exponents before I can multiply. So I can't multiply those together. A lot of you guys tried that in algebra 2, so don't do that. You're more mature, more mathematically mature, as I would say, right? You know not to do that. Okay, so what could be a different form of the answer, though? If this isn't a multiple choice test, maybe they don't have it like this. Here's another form. You could rewrite 1/2 as 2 to the -1. Do you agree with that? Right, 1/2 is 2 to the -1. Then what could you do with your exponents? Multiply them. So you could say you have 4 times 2 to the -x. That would be another form of the answer. So just know there's lots of different forms. I really should give a multiple choice test because I'm not preparing you for college if I don't. College, you don't get partial credit. I know this makes you sad. Right, unless you go to a really tiny liberal arts school, it's not going to happen. You're going to be in a room with like 300 people taking a pre-calc test, right? They're going to give you a multiple choice test. At IU, they always gave A through H as well. Very, very fun. All right. So number 1. So it says, use the graph of f of x equals 2 to the x to sketch the graph of each function. So let's start out with 2 to the x. Okay, if I'm finding 2 to the x, I could do a little t-table if I want to. All right, so I could plug in like 0, 1, 2, 3. So if I have 2 to the 0, I get 1, right? 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. What about 2 to the -1? What is that? 1 over 2, right? So as I graph it, I get 0, 1, I get 1, 2, 2, 4, and then it shoots up really fast to 8, and then half, and then, well, not half there. 1/2 and 1/4, and so on. So it's getting closer to the x-axis. Can I ever have 2 to some number equals 0? No, it never works, right? I'm never crossing the x-axis because of that. It's getting very, very close. Like 2 to the negative 1,000 is very, very close to 0, but it's not 0. So we go up like that. All right, so you guys thought transformations would go away. They really don't go away in pre-calc. Do a lot of transformations. So if I have 2 to the x plus 2, what happens? Yep, it just goes up 2. So basically you have exactly the same graph, except your new horizontal asymptote is going to be at 2 instead of 0. And instead of going through 0, 1, you're going to go through 0, 3. And you're just going to sketch it in. All right, what about negative 2 to the x? Yep, reflect over not the y-axis, the x-axis. So all of your y values are now going to become negative. So here, it's kind of tricky, so if you need to draw the original in like dotted lines, maybe that will help. Here's the original. Its reflection will go through 0, -1, and it will go down like that. And then what about 2 to the x minus 1? X is changing by subtracting 1 from it. So where does it go? What do you think? It goes to the right. It's going to go right 1. Right, because it's like instead of having f of x, you have f of x minus 1. That's what's happening. The x is replaced by x minus 1. All right, so you're going to go to the right one. So instead of going through 0, 1, we're going to go through 1, 1. But pretty much everything else is the same, right? The horizontal asymptote's the same. And it just shoots up really fast like that. Okay, so see how you can quickly sketch those without using two tables. As long as you know that first one, you're good to go. All right, so let's kind of discuss why you can't have negative 2 to the x. Okay, if I was doing a negative base, okay, when I do a t-table for it, if I plug in 0, I get negative 2 to the 0, which is 1. That works. Negative 2 to the 1 works as well, right? What's negative 2 to the 1? Negative 2. What about negative 2 squared? 4. Negative 2 cubed. Negative 8. Here's what happens for your graph. You get 0, 1. You get 1, negative 2. You get 2, 4. You get 3, negative 8, which is down there, right? Do you see how it's not an exponential function? Right? It's really weird. And don't even think about like the negative 2 to the 0.25, negative 2 to the, it gets really weird. Negative 2 to the 0.25, you actually wouldn't be able to do. It would not exist. It'd be the 4th root of negative 2. So that would not work. Hi. I do not. It's okay. All right, so the next thing. So we have 3 different functions, which you should already know. You should not have to memorize these. You should already know them. So the first one is the natural exponential function. This is f of x equals e to the x. E is a number. It's called the natural base. It's a little bit more than 2.5, like 2.718. It's around there. All right, compound interest. Do you guys all remember that formula? A of t equals p times 1 plus r over n to the nc. I always told you in Algebra 2 that you had to memorize it, and then I put it on your test anyway because I'm a nice person. I'm not nice in pre-calc. You need to memorize that. Yeah. I'm not. I'm the worst. All right, and then continuously compounded interest. Whenever something says continuously compounded, right, do you guys remember the formula? The PERT. So it's going to be A of t equals PE to the RT. So it's like not even every millisecond, it's more than that. It's continuously compounding. So this actually happens when you have any kind of growth or decay of a population. So if I have, you know, bacteria growing, it's not going to be like, oh, I'm going to grow for an hour, and then I'm going to stop. And I'm going to grow again once hour 2 hits. Does that make sense? It's continuously growing. Same with like decaying substances like carbon-14 and so on. All right, so here we go. So number 1 says, Michaela invests $20,000 at a continuous rate of 15% per year. Wouldn't that be amazing? First of all, if banks gave you a continuous rate, that would be pretty cool. They don't do that. Right, and then 15% per year, oh my gosh, that's a lot. So whenever you see a continuous rate, it's not actually like you're not gaining 15% at the end of the year, right? Because it's talking about a continuous rate. It's just, it's already worked in there for you. It's like the rate of growth, the yearly rate of growth with a continuous formula. It's kind of strange. All right, so anyway, so we have A of t equals PE to the RT, because we saw the word continuous. So we're saying, how much does she have after 3 years? The time is 3. She started with $20,000. She has E. Your rate is 0.15, right? Always write it as a decimal. And then the time is 3. So if you write it like that, that's fine on your homework. And on your test, it's fine. Just make sure you put it in correctly. So what I encourage you guys to do, and I did this last year as well, is to write it like this. So you know that you're going to do the 0.15 times 3 in parentheses on your calculator. Okay, so let's go ahead and try that. Did I say 0.15 times 3? Oh, yeah, 0.15 times 3. All right, so anyway, so we end up getting the amount after 3 years is $31,366.24. It should always make sense. If she's investing $20,000 and in 3 years only gets $18 trillion, you've done something wrong. You probably haven't done the 0.15, right? You probably did the 1.5. So think about it logically in the end. All right, number 2. So a radioactive substance decays in such a way that the mass remaining after t days is given by the function m of t equals 13e to the negative 0.015 t. So I gave you the formula. All right, where m of t is measured in kilograms. So t is in days, m is in kilograms. So it says find the mass at time 0. Can you do this without plugging anything in? Yeah. Yeah, what should it be? It should be 13 because this is set up in our PE to the RT formula. Grant, you with me? So this is our P. It's already set up that way. So if you weren't sure, you could do m of 0. And you would have, right, this becomes 0. So all that goes away. We get 13e to the 0, which is 1. We end up getting 13. It makes sense. It's the initial amount. So then it says, well, how much remains after 45 days? So we're plugging in 45 for t. So we get 13e to the negative 0.015 times 45. So we end up getting 6.619 kilograms. Should write kilograms there too. All right, always write your units. All right, and when in doubt, round to 3 decimals. That's always what you have to do in the AP Calc test. So if you guys decide to take AP Calc next year, it should always be 3 decimals. So get in that habit now. All right, so Michaela, from example 1, contemplated investing her $20,000 in a savings account at 15% interest per year, not compounded continuously. So it's just at the end of every single year, she's gaining 15% of what she had before. Okay, it's not going to be hugely different from the compounded continuously. I mean, compounded continuously is nice, right, for your money to constantly be growing. But it's not going to be hugely different. But she knows that it's not a good idea because it's probably not going to be as good as the other ones. So let's see. So it says, how much money would Michaela have after 3 years if her interest was compounded annually? So when you see compounded annually, and it doesn't say continuously, it says annually, monthly, daily, anything like that, you use the other formula. So this is the one that I told you you'd have to memorize. So P is 20,000. Your rate is 0.15 still. N is the number of times compounded each year. So how many times is it compounded each year? 1. It's at the end of the year. And then 1 times 3 gives the total number of times compounded. So if it was 15 years, it'd be 1 times 15, right? If it was monthly for 3 years, it'd be 36 up there because you do the 12 times 3. All right, so we figure it out. So we do 20,000, and we multiply by 1.15 raised to the 3. So we get $30,417.50. Write it like money. Pounds near a cent. So is it more than the last one? Yeah. So the last one, oh, wait. Did I make a mistake? I think I did this in the last class too. What did I do? R over N to the NT. 20,000, 1.15. I don't know what I did. Did you guys get the same thing when you plugged in? Yeah. I wondered too with this example because a lot of times. You got what? What'd you get?
I got 2,000 or 29,000.
I don't know. N is the number of times compounded each year. I don't know. I feel like I've had this discussion with Lori, who used to be an accountant, and he says the compounded continuously actually sometimes is worse because of the 15%. When you say 15% per year, you're not actually getting it 15% after every millisecond or whatever. But let me check that one in a little bit. I think I put it in right. 1 plus R over N. I don't know. So logistic growth function. So it says let A, B, C, and K be positive constants with B is less than 1. Okay, so this is the weird thing, logistic growth. This is the thing that you have not seen before. Okay, so for logistic growth, you are going to have 2 horizontal asymptotes. It's going to look weird. All right, this was one of the parent functions I kind of gave you before, like when we did the 12 parent functions. It's going to look like this. So it's going to go along the x-axis here. So you're going to have a horizontal asymptote of y equals 0, and you're going to have a horizontal asymptote of y equals 1. That's the parent function. We'll go through 1. And then this goes through 1/2 for the parent function. Okay, but the horizontal asymptote is not always y equals 1 on the right. So depending on your function. So, so you have these 2 formulas. I'll probably give you guys these formulas. But the big thing to notice is C is what we call the limit to growth. Okay, C ends up being the horizontal asymptote. So instead of writing y equals 1 here, I'm going to write y equals C. Because it's always that thing in the numerator. As you're doing these problems, I always want you to make sure that there is a 1 in this first location on the denominator. Do you guys see where I'm circling? There's a 1 there. If there's not a 1 there, you have to adjust it first before you can determine what C is. Okay, so there are going to be 2 important points. So always find the Y-intercept and the horizontal asymptote. The limit to growth, basically. Okay, so if you can find that top horizontal asymptote and you can find the y-intercept, you're good. That's all you really need to find for these graphs. Okay, so why is this function important? This function is every single population you ever talk about. Okay, it's kind of morbid, but this is true. So you guys know that the population of the Earth has been growing exponentially, right? No pun intended, exponentially. Do you guys agree? Like over the last few years, it's just kind of shot up. Will that continue forever? No. Why?
There's a point where they die.
Why are people dying? Carrying capacity. In other words, limit to growth, as it's called. What do you mean by carrying capacity? What will affect whether a population continues or not?
Resources.
Resources, exactly. So how much food we have and so on. So it's very morbid, but eventually the population is going to die off and it's going to flatten out at a certain number. Okay, I don't know what number this is. Hopefully, you know, we invent new ways of helping with farming and so on. I don't know. So basically that will happen with every population. It even happens with things like bacteria, which is super gross. You would think bacteria would continue growing and growing and growing and growing. It doesn't. Eventually there's a point when it starts to die off. So everything is like that, okay, where it has some kind of limit to growth, every population. All right, so we're going to look at these different functions. These are all logistic functions. We're going to try to make it as easy as possible. We're finding 2 things. We're finding the horizontal asymptotes. We're finding the y-intercept. That's all we need to sketch a graph. Okay, so it says sketch a rough graph of each function. All right, so when we look at this, is it set up in the first formula or the second formula? So if you guys look, going back there, does it have an E in it or not? It does not have an E in it. Okay, so it is set up in the f of x equals c over 1 plus a times b to the x. Okay, so if I'm identifying each thing, I first make sure there's a 1 there. There is. We're good. So when I'm identifying c, a, and b, c is 5, a is 4, b is 0.2. All right, c is always our limit to growth. The easiest way for you to see this is it is literally a limit. You don't have to write this down, but I want to at least show you. When you talk about the limit as x goes to infinity, what you're saying is you're going to continue to plug in bigger and bigger numbers for x. So let's say I start with a pretty big number, and I start with 100. Okay? If I do 0.2 to the 100 on my calculator gives me, for just this part right here, the 0.2 to the 100, it gives me 1.267 times 10 to the negative 70th. What is that? A very, very, very tiny decimal. It's like 0.00000. Lots of zeros, right? Very, very close to 0. So can you imagine plugging in 1,000, 10,000, 1 million, 1 trillion? Do you see how it's getting bigger? Like the 0.2 to whatever that big number is gets even smaller, smaller, smaller. Do you guys understand what I'm saying? So what we say is that this goes away. It goes to 0. So if the 4 times 0.2 to the 100 is gone, what do we have left? We have 5 over 1. What's 5 over 1? It's 5. So do you see why it's always going to be that numerator? Whatever c is, that's always going to be your limit to growth. Emerson, are you with me? All right, so it's literally a limit. That's why we call it the limit to growth. So as we draw this graph, we're going to draw a horizontal line here. Unless there's something strange, like maybe your original function had a -2 or something on the end of it, it didn't, then your horizontal asymptote, the other one's going to be 0. So let's think about that. If I'm talking about on the left side of the graph, I'm not thinking about x going to infinity. Instead, I'm thinking about x going to negative infinity. This would become 1 over 1 plus, or 5 over 1 plus 4 times 0.2 to the negative something. So let's start with 100. So let's go ahead and put that into our calculator. So get your calculators out. I'm going to do just the bottom. I'm going to do 1 plus 4 times 0.02, or 0.02 or 0.2? 0.2, right? Wrote that down wrong. 0.2 to the negative 100. Is it a tiny, tiny number, or is it a big, huge number? It's a big, huge number. So we have 5 over a huge. We have 3.155 times 10 to the 70th. That is huge. So if you have 5 over a huge, huge number, what do you get? It's going to be very, very tiny. It's going to be really close to 0. It's like that pizza example I told you the other day. Kind of gross. So this ends up going to 0. So what that means is, as I'm plugging in a really, really big negative number, I'm getting closer to the x-axis. So on the left side of my graph, I'm going to be over here. On the right side of my graph, I'm closer to the limit to growth. Okay, the last thing we need is the y-intercept. How do I find y-intercepts usually? What do I do? Plug in 0 for y, or for x, right? So I'm going to do the same thing. So I'm going to have f of 0 is going to be 5 over 1 plus 4 to the 0.2 to the 0, or times 0.2 to the 0. What's 0.2 to the 0? No, 1. So I get 5 over 1 plus 4, because it's 4 times 1. What is that? 1. All right, do you have some kind of hypothesis for what the y-intercept always is? It's always c over, no, it's not 1 always. C over what? 1 plus a. That is always the form for the y-intercept. You can memorize that if you want, or you could just easily plug in 0. It's pretty quick to just plug in 0. So that means we're crossing at 1. So we're going to go through at 1, and then we're going to do our little curve, right? And then go along the other limit. That's the logistic graph. So if you can get the y-intercepts and the horizontal asymptotes, you're good. All right, so next one, number 2. So do we have a 1 where we need it? We do, right? So we don't have to identify C, A, and B. I guess we do C. C is 20. That's always our limit to growth. So that is the horizontal asymptote on the right side. So I'm just going to do 20 and put it there. The other horizontal asymptote, like I said, is going to be 0 unless there's some kind of shift up and or down on the end.
So it's always going to be 3.
It's always going to C. The last thing we need to know is where the Y-intercept is. So you could do the Y-intercept is C over 1 plus A, or you could just very quickly plug in 0 for the X. So we get 20 over 1 plus 3, e to the 0. e to the 0 is 1. So 20 over 4 is 5. So we're crossing that 5. So it looks like that. Easy enough? All right, what's wrong with number 3?
There's a 2.
Right, there's a 2 there. We need a 1. So what do we think we're going to do on both the top and the bottom?
5 by 2.
Not subtract.
5 by 2.
Divide by 2. So we're going to divide the top by 2, and we're going to divide the bottom by 2. So when we do this, we get f of x equals 20 all over. So think about it. If I have 2 plus 5 times 0.25 to the 3x, and I divide by 2, I get my 1 like I want. What else do I get? Yeah, 2.5, or you could write 5 over 2. It doesn't matter. So 2.5, 0.25 to the 3x. Why did I not write 0.125? Yeah, it's like attached. It's attached to all of it. Think about numbers like if I had 6 times 4 times 3 and I divide by 2, like they were all being multiplied together anyway. When I'm dividing by 2, do I have to divide the 6, the 4, and the 3 by 2? No, because they're all being multiplied anyway. So really we just kind of reduce out and we're like, oh, 6 times 2 times 3, right? Does that make sense? That's what we're doing there. We're only taking it into the first part of this product in there. All right, so our C is 20. Our Y-intercept, are you guys getting really good at it? It's 20 over 3.5, which was what? 5 point. Yep. Right, so you could plug in, it's basically like these 3 numbers divided, like 20 divided by 1 plus 2.5. It's like you're ignoring that part that was in parentheses. All right, so we're going to get 20 for our limit to growth. 0 is the other horizontal asymptote, and then at 5.714, we have the Y-intercept. You what? Not really. That would be a very depressing population. Like where everybody's just dying. All right, number 4. So if I have f of x equals 85 over 5 plus 15 times 0.35 to the 2x. So let's think about what we need to do. Yeah, divide everything by 5. Did you guys know 85 divided by 5? Good. Did you do it on the calculator?
Yeah.
So we end up getting 17 over 1 plus 3 times 0.35 to the 2x. All right, so if I'm trying to find my limit to growth, I know that's 17. My Y-intercept?
5.6 would be
Yeah, so to do 17 over, well, no, 17 over 4, what's that going to be? 4.25. Did you forget the 1?
Yeah.
All right, so it's going to be 4.25 there. And it's going to do its little, like that. So what if you had a minus? I guess you could have like a minus in here. Like you could have 1 minus. What would happen then? I think it just changes your Y-intercept, but I think it still has the limit to growth that's the same. So I think it's just the Y-intercept's a little bit different. And it's been a long time since I've done logistic functions. I haven't taught pre-calc since 2009. It's a long time. All right, so the last thing is the one about Whoville. So I had you guys edit the numbers. So 20,125. So don't make it a decimal, make it a comma. And then 1 plus 579 e to the negative 0.034 x. That should be a t, I guess. T. All right, so what was the population of Whoville in I made lots of errors. It should be 1980. I wanted the starting amount. So what is the starting amount? In 1980, what did we start with? That's basically your Y-intercept. Right, it's saying what is the time, what did you have at time 0? So you're going to have e to the 0 then. So what was it? 34.698, so around, we'll say 35 people. You can round up or down for people, it doesn't matter. All right, what will the population be in 2050? So how many years after? A lot. That's the number. 70, right? So we're going to have, so we'll do this really quickly. So 1 plus 579 e to the negative 0.034 times 70. So I usually do the denominator first.
Turn around.
And then I do 1 over the answer. Or something divided by answer. So I got the denominator was 54.586. So if I do 20,125 divided by my answer, I get 368.679. So about 369 people. Okay, what is the city's maximum sustainable population? They're not growing very fast. They could grow a lot faster, couldn't they? 20,125. How did I get that? That's the limit to growth, right? So it's the C value. All right, so let me pass out your homework. I don't have your chapter 3 due dates, but I do at least have